Thank you all for coming to the first of our CLIMAS Colloquium for the year. My name is Dan Ferguson. I direct the CLIMAS program here at the University of Arizona. It's great to see so many members of the community joining us. The first thing I want to do is give you the caveat that this is a series of 3 talks about drought research that we've done. We're not necessarily positioned to talk about current conditions, which I understand is a concern for many people in the Southwest right now because it's been a dry winter so far. So in the panel part, we can chat a little bit about current conditions and how that fits in, but primarily what we're going to do is run through 3 speakers here. Connie Woodhouse is first from the School of Geography and Development and the Tree Ring Lab, and she's going to be talking about some recent work that she and her colleagues have been doing, looking at the impact of temperature on Streamflow. Dr. Chris Gitterman, who's also in the Tree Ring Lab, is going to talk about some work he's been doing with the forest and forests generally, but with the Forestry Department at the Navajo Nation, in collaboration with them. And then Mike Crimmins from Soil, Water, and Environmental Sciences is going to talk a bit about some of the work that he's been doing focused on rangelands and drought. So the big idea I had here in putting this group together was this is work that's been, all of this work has been going on for several years, in some cases many years of kind of building up to what we have here. The big idea was I feel like CLIMAS is positioned well to talk about a sort of interesting drought story that hasn't been put together completely. So that's kind of what we're doing here is we're trying to figure out, do we have a broader story than's typically told about drought in the region? And basically what I'm talking about is, so Connie's got this interesting stuff that her colleagues, she and her colleagues have kind of teased out about the role of temperature, air temperature and stream flow, which is something we don't talk about very much. Chris has really got some interesting work on the nation, thinking about how forests, high elevation forests, respond to drought conditions in differential ways. And then Mike, and I've been involved with Mike in some of this work for years, we're looking at how grasslands respond, and grasslands are so interesting because they're working landscapes here. So we're trying to figure out, can we synthesize these 3 things into a more complex story or more interesting story about drought in the region? Thus, we're here today. So these will be 3 shortish, 15, 20 minute, I think is what we're doing. Thoughts? 20-ish. 20-ish, Crimmins is last, so if he eats up all the time for the panel, then I will stand up and move him out of the way. And we're going to have time for a conversation discussion. But again, the idea is, can we synthesize some of this stuff into a story that we haven't quite told as a whole yet? So without further ado, oh, and I should say we have quite a few people online as well. So welcome. Thank you for tuning in. And during the panel part, Ben's going to, I think, help field questions. So if you're online and you would like to ask a question, feel free. It's the raise your hand thing and type in the box.
Chat box, yeah.
The chat box is how we'll take questions from the folks online. Okay, with that, Connie Woodhouse, take it away. And for the speakers, I kind of already told you, but if you stand about here, the camera still sees you.
And
You can use that. Or you can use
is
whatever.
arrow down?
Arrow down.
Okay, all right. Well, thanks for that introduction and thanks for joining us. I'm going to be talking about runoff efficiency, the impact of warming temperatures on Colorado River drought. And this is work that I've been doing with a number of colleagues over the past couple of years. Some of them are Adam Zank, Steph McAfee, Greg Peterson, and Greg McCabe, and Kiyomi Marino. And we've had work funded by the Department of Interior Southwest Climate Science Center and CLIMAS. So I'm going to run through some of the answers to these questions. What is runoff efficiency? What does it have to do with temperature? How does runoff efficiency influence drought? How has runoff efficiency varied over past centuries, and why is this important? My focus area is the upper Colorado River Basin. I'll be talking about that area in terms of climate, and then focusing on the streamflow gauge, Colorado River at Lee's Ferry. Is there a pointer? Maybe I don't need it. Okay, all right.
Sorry. It's your finger.
What is runoff efficiency? Runoff efficiency, which I'm going to abbreviate as REEs, is the relationship between runoff and precipitation.
Chris has a point for you.
All right.
Look at that.
Teamwork.
The
That's what I
advanced.
like about things.
Carry that around.
All right, so
Wait, it'll be there in a minute. It's a sliding answer too when Ben plugs that in.
I won't
Okay,
use it.
yeah,
So basically, we're talking about the precipitation that falls in the upper basin in the form of snow or rain, and how that precipitation translates to actual runoff in the river. And so there's a couple of different ways that this is defined. One way is as the ratio of flow to precipitation. Usually it's given in volume for a particular area, usually for water year. Another way is to look at the difference between flow and precipitation using standardized series. So for this study, we're looking at runoff efficiency as that difference between, in particular, water year stream flow for the Colorado River at Lee's Ferry and cool season precipitation for the upper basin. So we're focusing on cool season, not the water year. We're particularly interested in the relationship between cool season precipitation, snowpack, and water year stream flow. And we're using the difference instead of the ratio because we're particularly interested in the sign and the relative magnitude of those departures. So this is what the two series look like: flow in the dark line, precipitation in the blue line. These are in percentiles, so they've been standardized. This is 1906 to 2012. So we're looking at those differences. So what does runoff efficiency have to do with temperature? Well, there have been a couple of studies recently that have shown that runoff efficiency is strongly associated with temperature in the upper Colorado River Basin. And the thinking is that you have precipitation, some of it ends up in the river. What is explaining the rest of it? Temperature is a huge portion of that, but it's not the only portion of that. So an important caveat here is that temperature is not the only factor. In terms of that precipitation making its way into the stream flow, you've got things like base flows, groundwater, you've got soil moisture, and in this study, we're not looking at spring precipitation. So that's also another factor that will impact runoff efficiency that we're not addressing here. So let me back up a little bit and talk about the climatic influences on stream flow. This is from a paper that, actually this is a 2016 paper that we did in GRL, which looked at a really simple model of how climate factors, monthly precipitation and temperature, antecedent soil moisture, could be used to explain natural stream flow in the Colorado River. And we found that for the entire record, 1906 to 2012, 66% of the annual stream flow in the Colorado River was explained by April through October precipitation, so the winter snowpack. Only 8% was explained by March through July temperature, so sort of an extended runoff period of temperature. Soil moisture, a little fraction of that as well. So the take-home message here is that looking at all years in general, October through April precipitation is the big factor. Now, if you look at the years with the largest runoff efficiency value, they're positive or negative, so they usually years that had the biggest difference between precipitation and stream flow, we found that temperatures played a much bigger role. So in those years, we found that cool season precipitation only explained 90% of the variability, and runoff season temperature explained 42%. So we're interested in those years in this study where we thought that runoff efficiency had the biggest impact, where temperature had the biggest impact on stream flow. So for most of the rest of the talk, I'm going to be talking about runoff efficiency, but only those years that have the largest value. So those years where the difference is the largest between stream flow and precipitation. So here's a graphic that shows those years with the largest RE values. The blue ones are the positive RE values, those years that have more runoff relative to precipitation in blue. And the pink ones are the years that have less runoff relative to precipitation. So you can see this sort of pattern. There's a lot of clustering of blue here, clustering of pink here. There's actually 4 different kinds of, or flavors of runoff efficiency. Of those that are positive REs, there are some that occur under above average flow years and some that occur under below average flow years. So an example of a positive RE, we have more flow than we might expect relative to the precipitation in high flow years. 1921 is an example of that. RE positive again, but with below average flow years, 1953. And then for negative RE, again, where we have less runoff than we might expect given the precipitation, we have years that have above average flow, 1999 is an example, and below average flow, 2004 is an example. So if we look at how those are distributed, along with the temperatures that are related to those, we can see a clustering here. I'm not sure if the colors show up so well. These are the high flow cool years, a clustering of those in the early part of the 20th century. The low flow cool years, those are hard to see in this graphic, but there are a few around. I can't see them. I don't know if they're visible. Then we have high flow years that are warm, a couple here, but we see more of these kinds of years here. And then low flow warm years clustering at the end of the record. So 4 kinds of RE years. Okay, so how does runoff efficiency influence drought? You might be getting a sense of that now. But if we look at the major droughts on the Colorado River at Lee's Ferry, this is what they look like. And I'm defining drought as below average flows, consecutive flows broken by no more than 1 year of above average flow. So when we define that, this is the Colorado River record naturalized flow at Lee's Ferry. We have the 1930s drought, we have the 1950s, a drought in the 60s, a short period in the 1970s, the late 80s and early 90s, and the drought since 2000, and this record goes up to 2012. So those are our droughts. Now, if we look at temperature and precipitation during those drought periods, along with water or stream flow, we get a sense for the roles of precipitation and temperature during those droughts. So what I'm showing you here is each drought is color-coded, and then we're looking at 3 variables: water or stream flow, cool season precipitation, runoff season temperature, and those variables are averaged during these drought periods, and they're plotted in percentile. So for water or stream flow, here are all those periods of drought. Their average annual deficits or percentiles are pretty similar. They're between maybe 35%, 40%. The 1970s has the highest. So they're all pretty similar. If we look at the cool season precipitation, we see much more of a range. Our driest drought is the 1950s. Our most moderate with regard to precipitation is the most recent drought, where really we're close to the median here in terms of average annual precipitation for that drought. And then when we look at temperature, we can see that while the 1950s was our driest drought, it was also our coolest drought. And our warmest drought was the most recent drought, up at about the 80th percentile. So how does that relate to runoff efficiency? These are the values of runoff efficiency. As you might expect, our most negative values are the most recent droughts that are the warmest. 1950s is actually slightly positive, which means that we're getting, even though it's a dry period, we're getting a little bit more stream flow that we might, relative to the amount of precipitation. The 1930s is more negative. That's the 1960s, and then 1970s is kind of a zero value, the negative or positive for the runoff efficiency. So we see that basically during some droughts, runoff efficiency may ameliorate the impacts of precipitation deficits on stream flow. If it's a positive, it might actually, because temperatures seem to be cooler, might actually make those precipitation deficit impacts on stream flow a little bit less, while in other cases, RE and warmer temperatures may exacerbate the impacts of these deficits. So how has RE varied over past centuries? This is work that Greg Peterson and I have been doing. It recently came out in this 2008 paper, where we've reconstructed, we've developed an RE based on reconstructed variables from tree rings. So we're using a reconstruction of stream flow that exists. We developed a reconstruction of cool season precipitation for the Colorado River Basin. We took the difference of those two series and we developed a reconstructed RE. And so here's the reconstructed runoff efficiency series in blue, the observed in red. They're not exactly the same, but they track pretty well. This is a really big challenge for tree rings. We're asking the tree rings really not only to reconstruct these variables skillfully, but then to subtract them and to find something that looks similar to what we see in the instrumental record. These again are the 1 plus or minus 1 standard deviation threshold. So again, we're looking at the values that fall outside of these, those that have the biggest difference. So there's a couple things going on here, but the main part is here are 4 flavors of runoff efficiency here, color-coded. These are the ones that concern drought, where we've got below average flow in positive RE years, below average flow in negative RE years. Just looking at these colors, it's a little hard to pick anything out. You can see these kind of green, clusters of green are wet years that are cool. And these are the droughts. So again, defining droughts in the reconstructed stream flow as those consecutive years broken by no more than 1 year of above average. And here's pluvious. Oops. Must have hit the arrow. So let's take a little closer look at these, since they're a little hard to digest in that form. What we're going to do is do counts of those types of years, the 4 types of years, by half-century period. So these are all half centuries. This one's a little bit less than half a century. So this is just 1 year less. And first looking at the positive runoff efficiency years, particularly the low flow ones. So again, these are years where we have more runoff proportional to the precipitation, but during dry years, below average flow years. And here's how they are arranged in 50-year periods. And we see, if we're trying to evaluate the last 50 years of the 20th century, we don't see anything popping out that shows that those are unusual. We see a lot of variability in these counts. We see very few of these extreme RE positive years in the early part of the record. One thing overall we do see is a decrease in positive runoff efficiency for both categories over the last couple of centuries. And then here are the negative runoff efficiency counts by half-century periods. Looking at the low flow, so these are years where we're getting less runoff than we might, proportional to the precipitation. Flow is below average. Here are the last counts for the last, the 20th century. And actually these, if you add these up, there are fewer cases of these than any other century. We're focusing on drought, but if we look at this category where we have high flows, but less flow than we might hope to get from precipitation, we find that we've got a larger number of those years in the 20th century. Otherwise, there's, overall, there's not really a pattern that says, oh, we're, in terms of negative runoff efficiency, we don't see any kind of trend like we're kind of seeing there. So the last thing that Greg and I did was to look at the temperature reconstruction. Now, we are using the difference between precipitation and runoff in the reconstruction to infer temperature. And I've already said that temperature is not the only factor that affects runoff, but it seems to be an important one, particularly when you look at those extreme runoff efficiency years. But we also wanted to kind of ground truth it with a record of temperature reconstructed. So Greg did a temperature reconstruction, that's in the orange line here, which is a little bit, the trees are not quite as good at giving us temperature information as they are at moisture information in this area. And so this reconstruction is for May through July. There's really no information from trees in March and April, which are really important to that, to the temperature, the season of temperature that's important for runoff. And the scale of this reconstruction is not very high. There's not explained variance. The amount of variance in the temperature record that this reconstruction is explaining is not very high. It's 50% or less. Our reconstructions of streamflow are something on the order of 80%, precipitation 70%. So it's not, there's uncertainties in this record, but we thought we'd look at it anyway. The blue line is runoff efficiency counts. So we're looking at 20-year running counts of those most extreme runoff efficiency years and plotting them. This doesn't tell us much, but if we put it together with the streamflow record, we can start to see those different categories and how runoff efficiency might be affecting streamflow, and then kind of ground truthing out with what we think might be happening with temperature. So for these green peaks, which again, don't look green in this image, but these are the periods of time where we have positive runoff efficiency, we have high streamflow, and we tend to have cooler temperatures. So our biggest peaks in streamflow seem to be enhanced perhaps by cooler temperatures. These periods where we have some of our biggest droughts, but not all of them, several of our biggest droughts, we have negative runoff efficiency and warm temperatures, which suggests that those droughts are exacerbated by warmer temperatures. And then we have this period, which looks orange in my PowerPoint, but looks pink here, is that we have high flows. This is the end of the 20th century. We have negative runoff efficiency and warm temperatures, suggesting that even though we have high flows, they're not as high as they could have been where temperature is not so warm. And then finally, one case here where we have reduced flows, below average flows, but we have cool temperatures and positive runoff efficiency. The one case where we're seeing some of these individual years, but one period of time where it looks like this drought could have been worse were these temperatures warmer. But because we have that positive runoff efficiency, that's probably ameliorating the impacts of that drought. So what does this all mean? Basically, temperature modulated runoff efficiency has been a consistent influence in the Colorado River Basin over the past 4 centuries. It influences streamflow both in positive and negative ways. However, because of this relationship between temperature and runoff efficiency, as temperatures warm, there are really implications for how temperature is going to affect streamflow in both high flow and low flow years in the future. And we're already seeing evidence of this. The reconstruction only goes up to 1997 because we're limited by the streamflow reconstruction that we used and the chronologies that went into it. But if we put the reconstruction record together and also see what we're looking in at the instrumental record, we can see this evidence of warmer temperatures impacting both high flow and low flow years. So sort of a sense of what might be coming in the future. And that's all I have. Hopefully that was 15 minutes.
It was almost exactly 15 minutes.
All right,
Of
great.
course it was, Connie. Thank you. Maybe what we can do is take a quick, do you have a quick clarifying question for Connie before we move on to Chris?
I have a clarifying question.
Please.
Just for the beginning part, when you're looking at instrumental temperature, was it annual or spring or what was?
For temperature is runoff season temperature, so March through July.
Okay, so Connie gave us part one of the story. In a nutshell, warmer temperatures may in fact exacerbate drought conditions in a stream flow.
Yes.
In a stream. Okay, Chris, part two. Is this already queued up then?
It's the next one.